I will now introduce our last speaker of this afternoon, Professor Martin Siegert. He is a professor of geosciences and the co-director of the Grantham Institute for Climate Change and Environment at Imperial College London. Previously, Professor Siegert was the director of the Bristol Glaciology Centre at the University of Bristol, head of the School of Geosciences and assistant principal for energy and climate change at the University of Edinburgh, where he led the creation of the Edinburgh Centre for Carbon Innovation. With a PhD in polar sciences from Cambridge, his research interests are in the field of glaciology, and he uses geophysical techniques to quantify the flow and form of ice sheets, both now and in the past. In 2007, he was elected a Fellow of the Royal Society of Edinburgh, and 2013 was awarded the prestigious Martha Tinker Muse Prize in Antarctic Science and Policy. Let's welcome Professor Siegert.
Well, good evening, and many thanks for that very kind introduction, and to Enrico and Pedro also for saying quite a few things that I was going to say, and that's no problems. It leaves me time to say something else. It is a bit cold in here, isn't it? Yeah, but so we're going to the polar regions, so it's kind of fine to do that. I'm going to be talking about the urgency of climate change. I'm going to be talking about taking action, and I'm going to be talking a little bit about the role of universities and what we need to do as well. But there is me. I'm in the centre, pretty much, of West Antarctica, and that's where my research takes place. And I've been doing it for 30 years, and by looking at the polar regions, which are warming at least twice as fast as anywhere else on the planet, I got passionate about climate change. And glaciology is an amazing subject to work in, and I'm very privileged to do it. But the challenge of climate change requires us all to take notice of it and work together for the solutions. So I'm going to a bit of history. Why not? This is Louis Agassiz, and he was a Swiss naturalist. And Louis Agassiz went round places like this. This is taken from my summer holiday that I had in Switzerland. Any ideas where that is? Zermatt. So the Matterhorn is right behind me. And he went to places like this, and he looked at the morphology. And he basically said, I think I understand what caused this landscape. And I think it's the action of glaciers. So the other way to look at that is that valley where Zermatt is now positioned once had an enormous glacier within it, and it was eroding the side walls of that valley. And now we understand that's pretty straightforward, right? It's like textbook stuff. But of course, in the middle of the 19th century, no one really understood that. This is the Finnish balancing rock. What did the Finnish people think was responsible for that? They claimed a giant put it on the top, right? Well, Louis Agassiz went to Alex Glacier in Switzerland, and he looked at this glacier in some detail, and he saw huge boulders, he saw erosion taking place, and he put his theory together that there were many parts of the planet, mountainous regions around Europe, that show signs of glaciation. That means at some stage in the past, the world was a lot cooler, and what that means is from some stage in the past to today, the world has got a lot warmer. This is a picture of the Görner Glacier. It's my picture. And I held a tourist guide up against the glaciers you can see in the background from about 5 years ago. And those glaciers are noticeably smaller than they were just 5 years ago. So they're going back at about 10 meters a year or so. And there's a wonderful Matterhorn in the background, and there's an amazing glaciated landscape. There's no reason for me to show you this apart from their lovely landscapes, and it was my holiday, so it looks nice memories. But this is in North Wales, and if you ever get the chance to go to North Wales, this is Snowdonia, And this is a place where Charles Darwin visited twice. Now, Charles Darwin was a very interesting character. The common orthodox view of this landscape was, in 1850, was not that it was carved by glaciers. What was the sort of common scientific orthodox view of what was responsible for that landscape, you say? You should be asking me questions. I'm asking you the questions. So who's thought of it? Well, I'll tell you, in the Western Europe at least, the orthodox view was that it was given to us by God. Fair enough. And so when Charles Darwin visited this place, which is actually really interesting, it's got signs of glaciation all around it. He went there first and he didn't see it at all. But he went there again and he was completely convinced. But this was amazing stuff because they're challenging the word in the Bible, which is what everyone is being told. So these were amazing times in the middle of the 19th century. And it transformed all the scientific ideas about the way that we see the planet, of course. You can't really see this inscription, but it's a beautiful inscription. And it says words to the effect of, Charles Darwin says, I didn't see it when I visited the first time, but the signs of glaciation were all around me. A house burned down to its foundations couldn't tell its tale as well as this valley did. So basically what he's saying is a house that had burnt down is obviously was a house before. And when you go to that valley, you can still see the signs of glaciation all around. It's a lovely quote. So Louis Agassiz developed this idea called glacial theory, and the world was a lot colder in the past. But why was it colder in the past? So the first people to put some ideas on this was James Kroll. James Kroll was from Glasgow. We'll be in Glasgow this time next year, COP26, of course, for the Italian-British joint presidency of the COP process. Looking forward to that. And he was a self-taught mathematician, and he said, I understand how the Earth rotates around the sun. It's not a circular orbit, it varies, and I can calculate with some precision the amount of solar radiation coming into the planet, and sometimes there's more, and sometimes there's less, and when there's less, we get an ice age. And everyone heralded this as, that's the explanation for why we have an ice age. And of course, then someone pointed out that his date for the ice age was far too far in the past, and he died without anyone believing his theory. It's kind of a sad story, really. And on the right-hand side is Milutin Milankovic, a Serbian mathematician. He revised Kroll's idea, and he got the calculations right. It wasn't actually that Kroll got them wrong, but they were kind of refined by Milankovic. And everyone thought, oh, well, that's it. We've got it. We've cracked it again. It is solar, the way the Earth orbits around the sun. That's what causes ice ages. Until someone pointed out that the amount of the difference between the maximum and the minimum amount of solar radiation coming onto the planet through this process was teeny. It's like a few percent. That's it. And it's not enough. It's not enough to cool the planet 4 degrees and then warm it by 4 degrees and cause the massive ice sheets to grow and shrink. And so he died without anyone believing his theory as well. So we need a time machine, and the time machine is the Antarctic ice sheet, as has been explained previously by Enrico and Pedro. This is Vostok Station, the middle of East Antarctica. The further down the ice you go, the older it gets. The ice has got little air bubbles in it. Those are time capsules of the atmosphere for when the ice was once snow. And you can take it out, and you can measure it, and this has been talked about before. 180 parts per million carbon dioxide in an ice age, 280 parts per million in an interglacial. And they have to go back, 700,000 years, and that still holds. Until about 1850, where we started burning fossil fuels at an industrial level, and now the CO2 is over 400 parts per million. That's the hockey stick, famous hockey stick. It's getting warmer, noticeably from the Industrial Revolution, and you put the CO2 over the top of the temperature record, and there's like a 1-to-1 correlation. It's difficult to see how you can be skeptical about climate change when you see this information. In fact, very few people are skeptical about climate change. And there's the Mauna Loa Observatory, beautiful record. Not only is CO2 level in the atmosphere going up, it's going up at an increasing rate. Now, why are we focused on carbon dioxide? It's not the only greenhouse gas. There are many greenhouse gases. It's not even the most potent greenhouse gas. Methane is many times more potent a greenhouse gas than carbon dioxide. But carbon dioxide's got a special trait that is worrying, and that is when it gets into the atmosphere, it stays in the atmosphere. So this is a complicated curve, but don't worry too much about it. The top, think about the red lines. The top one is the amount of carbon dioxide that we put into the atmosphere. And this, unfortunately, is the pathway that we're on right now. Let's just pretend we just keep putting carbon dioxide into the atmosphere, and then by a couple of hundred years' time, we're going to have 2,000 parts per million of carbon dioxide in the atmosphere. It's, you know, it's kind of a bit fantastical, but let's just say that that's what we do. And then we cook the planet by doing that, and so we turn it off. Well, the bottom graph shows you the level of carbon dioxide in the atmosphere after we've turned off the carbon dioxide, and you can see it stays in the atmosphere for 1,000 years or more than that. This is why we talk about climate change being intergenerational. That's why the amount of carbon dioxide going into the atmosphere now, unless we do something, will stay there for decades and centuries. And that's why it's tomorrow's problem, our children's problem, and their children's problem. We're creating it, and it's the future that we're influencing. So it's not the first time that the Earth has had 400 parts per million. We've had it before, but you've got to go back 5 million years. 5 million. We are the only humans, the first humans to be breathing air that has a carbon dioxide concentration of over 400 parts per million. And next year, we'll be the first humans to have carbon dioxide levels at 415 or whatever it is, because this keeps going up. So it's like we're breaking records every single year. It's not a record that we should be proud of, but we are. The Pliocene was very interesting because that was what the Antarctic ice sheet looked like. Sea level was about 20 meters higher in the Pliocene. Temperatures were about 3 or 4 degrees warmer than they are now. If we keep burning fossil fuels at the rate that we're currently doing it, just keep burning fossil fuels, by the end of this century, 2100, there'll be 1,000 parts per million in the atmosphere. 1,000. We had that before. It was 55 million years ago. 55 million years ago, Antarctica today on the left-hand side, 55 million years ago on the right-hand side, there was no ice on the planet, and temperatures were somewhere between 8 and 12 degrees warmer. So let's just take those two things into consideration. When we come out of an ice age, you go from 180 parts per million to 280 parts per million, and it took the Earth about 10,000 years to increase the level of CO2. The ice sheets melted, the sea level rose by 120 meters, but it took 10,000 years. Now, I'm 52 years old, born in the 1960s. Since the 1960s, we've put in 100 parts per million of carbon dioxide. It took the Earth 10,000 years, we've done it in 50. 55 million years ago, when the Earth had 1,000 parts per million, that was a very interesting time geologically. There was a lot of volcanic activity, huge amount of volcanic activity, and the atmosphere was getting very concentrated in CO2. But it took somewhere between 10,000 and 20,000 years to do that. Geologically speaking, that was very quick, but that's how long it took. If we keep going with the rate of fossil fuel burning that we're currently on, and just keep going for another 80 years, we'll get there. It took the Earth 10,000 to 20,000 years. We'll do it in 80 years. It's not necessarily the end conditions that I'm worried about. I am worried about those. It's the rate of change of the planet. It's unparalleled. We have not warmed the planet through carbon dioxide this quickly ever before. This planet has never seen a sudden injection of carbon dioxide in the atmosphere as quickly as we are putting it in. And that's why we should all be really worried. This is a greenhouse gas that will stay around for a long time. And if we don't do something about it right now, in the next 30 years, then our children's future and their children's future will be impacted. So it's our challenge. And a way to kind of look at it is, think of it this way. How would you want to be regarded by the future generations? I think about it like this. I'd like to be thought about as being a good ancestor. Looking back in this time, I'd like people in the future to think about us as understanding this problem and doing something about it. But we've got a choice to make. One is that we tackle it and we get on with it seriously, and we'll be regarded very well in the future because it's the right thing to do, or we can just not rise to the challenge. And I think if we did that, we'll be looked upon as bad ancestors. So the choice is ours. Thank you.
Thank you, Professor Siegert. Do you have questions? There's someone down here. Can someone get the mic here, please? Meanwhile, I think I'll pose a question or more of a comment. I mean, the planet in the end, with all the CO2, will turn out fine. Right?
Is that a question?
Because, no,
Yeah.
I mean, it will turn out fine. The whole concern here is what will happen to us.
Oh, okay.
Right? Because it's been green and beautiful. It's been very icy. It's gone through all these stages for the whole history of the Earth.
Yes.
So even the planet will be fine, but we won't be fine.
Well,
right?
So I think, as Enrico pointed out in the first talk, the last 10,000 years is the Holocene. And CO2 has been very stable. Earth's climate has been really stable in that time. And coincidentally, that's how our societies and civilizations have been established. So we've got cities and roads and transport and agriculture, and all of that has been imagined and implemented in a climate that is not dissimilar to today's. And what we're doing is a crazy experiment to see if we can live on the world in the way that we're currently doing it with a climate that's completely different. And of course, that's a stupid thing to do, because in a climate that's completely different, you wouldn't put the towns and cities in the same places necessarily. You wouldn't put the agriculture in the same places necessarily. So there'll be huge upheaval that will take place as a consequence of climate change. And competition for resources will happen, and conflict will happen. Barack Obama said this is the greatest challenge that humanity is facing. And he kind of didn't do that, I suspect, because of the scientific evidence on climate change. He did it because of the fear of conflict. And climate change mitigation is another way to look at that, is to avoid conflict. And really, we absolutely should be focused on that as well. Thank you.
Firstly, thank you for a brilliant presentation. Exists, to your knowledge, some technology to remove the CO2 from the atmosphere today?
Yes. Trees. They're wonderful. Trees do it, as Enrico was saying. And so do wetlands. And so do marine forests. The greatest carbon dioxide sink that we have on the planet is the ocean. And in fact, no one's actually said, why did the carbon dioxide go up from the Ice Age to the present day? But I know that's on someone's mind, so I'll tell you why that was. It's the ocean. The ocean absorbs about half of how much carbon dioxide that we emit right now. It goes into the ocean. It does us an amazing favor. Without the ocean, we'd be warming up much, much quicker. Now, we take it for granted, and there's ocean acidification resulting, and ocean warming resulting, and it's a bad thing. But to this point, they're doing a great favor to us. But here's the thing. There's a feedback process. When you start to get warmer, as the Earth starts to get a little bit warmer, the ocean's going to get a bit warmer as well. And as the oceans get warmer, they get less productive. Fewer things grow in them. And if fewer fish and organisms are living in the oceans, then they'll draw down less carbon dioxide from the atmosphere. And so you can see, as things get warmer, there'll be therefore more carbon dioxide in the atmosphere. Why do they do that? It's quite straightforward. Warm ocean water is quite buoyant, and so it doesn't get replaced by water from underneath it so easily. Now, the water from underneath it has got lots of nutrients in it, and so if you can get that water to the surface and get it mixing with the sunlight, then you get a lot of life developing. So the converse is true when it gets colder. As the Earth starts to get colder, the oceans get colder, that cold water sinks and gets replaced easily by the nutrient-rich midwater, and a lot of life happens. The richest ocean in terms of life in it on the planet is the Southern Ocean around Antarctica. So much life is in it. And it's because cold water sinks, gets replaced by nutrient-rich mid-depth water, interacts with the sunlight, and life happens, and the CO2 is drawn down. That didn't answer your question. Didn't answer your question. That's my answer anyway.
Thank you for a very compelling, here I am,
Down here,
Right.
down here.
here,
Oh, yes, gotcha.
Yeah. For a very compelling presentation. You have alluded in your introductory remarks that there are some people out there who don't believe in what you were describing. Unfortunately, some are leaders of relatively important countries. Playing a little bit the devil's advocate and looking back into the history of science, you would dig out many predictions in the past which have proven, in many instances, fortunately, wrong. So how sure can you be, and actually that was a question which I would have had to the previous presentator, how sure are you about what you're telling us
Absolutely.
now,
Yep.
given the fact that the world is extremely complex, and if you look at the weather forecast, it's still beyond the very modern science,
Well,
still not as predictable as we would like to
that's
have
a
it.
very
So
good point. So why don't we start with weather forecasting, which is spectacularly good, in fact. So check out Storm Harvey, Hurricane Harvey, which was predicted days in advance of it hitting Corpus Christi in Texas, and that wave, that arm coming around, hitting Houston. Several days before that actually hit, they knew what was going to happen. And the reason they knew it was going to happen is because we understand the physics of the atmosphere and the ocean, and our very sophisticated models using those physics was able to produce it. It was a very, very good indication that we understand how this works. And it's the same type of physics and understanding which allows us to go back further in time and to speculate, use the models to speculate what's going to happen into the future as well. First person to talk about carbon dioxide as a greenhouse gas was Eunice Foote, often forgotten about American scientist that regarded carbon dioxide as a greenhouse gas. And the great thing about it is you don't need much greenhouse gas to have a big difference. The radiative forcing of just a little bit of greenhouse gas change is enough to cause the difference between an ice age and an interglacial. 100 parts per million is all you need to cause the changes that we have seen. So our appreciation of the physics is like fundamentally understood and is demonstrated pretty much every time that we see weather forecasts. I mean, weather forecasts in the 1970s were dreadful, right? As a boy growing up, you know, always take your umbrella. Well, you're in London, always take your umbrella when you're in London. Of course you do. But these days, actually, they're pretty good, weather forecast, and that's because we understand the physics really, really well.
We're going to resume this question session. Let's thank Professor Siegert again.